So our speaker is Felipe, and he is a physicist from Chile who studies what planets are made of deep in their interiors. He earned his PhD in physics from the University of Chile in 2015 and is now a scientist at UC Berkeley in the Department of Earth and Planetary Sciences. Felipe is part of a research team that uses powerful computer simulations to explore and predict how materials behave under the extreme pressures and temperatures found inside planets, conditions that are often impossible to reproduce in a laboratory. By simulating matter at the atomic level using quantum physics, Felipe investigates how planets form and evolve and what they're made of deep inside, from rocky super-Earths to gas giants like Jupiter. His research has revealed how ingredients like rock and metal interact under intense conditions, including how rock can dissolve into metallic hydrogen and how planetary cores might slowly crystallize over time. Felipe has received several honors for his research and scientific service, including fellowships from Chile's National Science Agency, CONICYT, and recognized twice by the American Geophysical Union for his outstanding work as a reviewer of scientific articles. And so we are very honored to have Felipe González tell us all about our planetary interiors.
Thank you very much for that very kind introduction, and thank you all for being here. I'm really happy to be here with you, sharing all this research that we're doing in the Earth and Planetary Science Department, which I feel really passionate about because it's something that is really cool, it's really novel, and we're really pushing the field to the new era of planetary science. And it has to do with what you're seeing now on the screen: these planets. But in particular, what's happening in the interior. So inside a rocky planet, we imagine that there are like several layers of materials made of something, right? And at the center, there's a core that is made of probably different material. And we want to explore what's happening with these materials at the extreme crushing pressures that they have at their interior. And that's why we need properties of minerals that we can simulate with quantum physics at the atomic level to predict what these materials will do at the extreme crushing pressures of these planetary interiors. So when I asked ChatGPT to draw a picture of what I was going to talk about today, he drew this thing, which is kind of crazy, but it has some things that are accurate. So for instance, it drew like more than one planet, which is kind of the case. When astronomers find planets, they're generally in planetary system. There's not just one orbiting the star. And the planets seem to have like this type of layers that are somehow like connected to a gradient in temperatures, right? These layers inside the planet are very hot. And there seems to be the idea of ChatGPT that there's something with the atoms happening here, right? So there's some chemical interactions. There are novel phases of matter appearing. The electrons behave differently, forming new phases of matter. So he got it like kind of right. So that's more or less where we are heading to. But before I get into the science, let me tell you a little bit about myself. I come from Chile, which I guess makes me American because I'm like South American, right? Turns out it doesn't help me with the green card. Anyway, so the thing is that I did all my studies in the Universidad de Chile, where I did my bachelor in physics and PhD in physics, and ended up here in Berkeley doing a postdoc. I will tell you more about it later. And I grew up in a very little town where this was literally my backyard. So this is like being at the bottom of the Grand Canyon. Basically everywhere you see around is just mountains. I feel like kind of trapped, but it was trapped in a cool way because you got like these amazing views. This was summer and this was winter. So you see like it was snow all year long because the altitude is like 8,000 feet, which is more or less like the altitude at which you jump from a plane when you do skydiving, right? Which I did once. And you get these like breathtaking views of the mountains like every single day, and you can climb these mountains, but you don't get that far because they're extremely high. Little did I know that I was going to be studying those rocks and like the origin of those rocks later in my life. And in this little town, I had to commute every single day from here, that you can see literally like trapped in the mountains, to the nearest by town here to get my education because there was no elementary school over there. So this was like 40 minutes commute every single day around like very dangerous cliffs on the side. And I did my high school there and my elementary school. And back then, like my main passion was music. So here you see a very hairless version of myself playing with my guitar. And in particular, I got into metal, which you can identify by the Iron Maiden posters in the background there. And I still carry my passion till this day, playing my guitar in more days, more hairy now. And I'm actually like so much into metal that I chase bands around the world to take pictures with them because I love them so much and I like to take pictures with them every time I see them. And it makes me really happy to be part of this metal community besides my scientific community. And in fact, I love metal so, so much that I went into a cruise in the Atlantic Ocean called 70,000 Tons of Metal, which is a cruise that lasts for 5 days where you listen to metal 20 hours a day. You get the chance to see like 60 bands, and it's like concerts all day long. You just have 4 hours to sleep before the next concert starts. And if you've ever played Guitar Hero, you may recognize the heroes from Dragon Force, who composed the song Through the Fire and Flames. That's one of the most difficult and most known songs of Guitar Hero. Oh, they were there just hanging out. Really cool dudes. So it was like a great week. But anyway, it's just really crazy. You can see like people like crowd surfing there, having the greatest time of their life. And you're just in the middle of the ocean listening to the loudest music. This is just one of 5 stages in the ship. So this thing is crazy. And it was really nice stuff. But let's go back to the science. So that's one side of me. I did my PhD, as I mentioned, in Chile, and I was advised by my PhD advisor to apply to scholarships to go abroad. So like expand my horizons. And I applied to a scholarship that was specifically dedicated to do research abroad. You couldn't do research in Chile. So that was really a pivotal moment for me because it opens the gates for me for new research, new perspective, things that are not done in Chile at all. There was nobody in Chile doing this research. And I found it really cool by reading that there was someone here in Berkeley like doing actually what I want to do in my PhD. So that's how I found it. I applied to the research. I came here to do a short stay, then going back to Santiago, completed my PhD. And then afterwards, it was like a natural call to go back for a postdoc. I really wanted to be back here. So I've been in the Bay for quite a while. And the Berkeley is connected to Livermore, which for those of you who don't know where it is, by a very specific reason that will be clear in the talk, because here in Livermore, they have the National Ignition Facility. This is where it was going to be installed. And the goal here is to generate nuclear fusion. But this machine, which is the most powerful laser in the world, can generate the conditions that I need to explore planetary interiors. And I will explain that in a little bit later. So when I was assigned to read like a couple of papers for my PhD, I found this one, which is one of the first papers that I ever downloaded. And you can see keywords here. First is prediction. So these guys were able to predict that a new phase of silica, which is basically sand, affecting the stabilities of the silicate, magnesium silicate rock, which is one of the most abundant minerals on the Earth mantle. And somehow this is happening at multi-megabar pressures. That means literally many millions times at the pressure that we feel here in the atmosphere. At the bottom of the ocean, you don't even get like even a tenth of a million. But at the center of the Earth, we have 3 million atmospheres. So nobody knows how matter behaves at those extreme conditions. And there was like a push to investigate what happens to the matter that we know, but at these conditions where it has never been seen. And they were talking in the same paper about these new exoplanets, these super-Earths that were recently discovered. And they wanted to investigate not only like the history of formation of the Earth itself, but these new planets that were appearing that astronomers were reporting called super-Earths and other types of planets. And little did I know that with time, like a couple of years later, I would end up having dinner with Taku and Junsu Chiya in this picture here. So now part of this like beautiful community that's trying to push it forward. And that's how I come with this reading with my PI, Burkhard Milzer, who is sitting here with me in the picture in the Department of Earth and Planetary Science, who has studied in very great detail what's happening at the interior of Jupiter. So I ended up like doing research about the Jupiter's interior. So I literally felt like I was being picked up by my rock stars from the audience, and now I get to be like a part of a band like of science doing rock on the stage with them at the cutting edge of science. So it's really cool feeling to be part of this. So This is a picture I wanted to include that I took a few years ago at this astronaut of the Campanile here and of the moon. I literally put my phone on the telescope, so that's something that you can probably do tonight if you're lucky, and get this like really high resolution picture of the moon, where you see the craters and these different areas of the moon that immediately makes me wonder. It's like, what are they made of? It's like, why is it different? And where does this material come from? It's like, how do we know like what this moon is made of? And what's even beyond the moon? Well, what happens with other planets that are around? And it turns out that nowadays you can go to the NASA website, Eyes of Exoplanet, and you can literally see the skies of Berkeley from this program that is online. You don't even have to install it. And pick a star, let's say, let's pick up that star over there. And these are all stars that have exoplanets that are known. And you can click on those stars and it will take you to that other solar system very far away. And it will show you the different planets that are orbiting that star. And you can click each of the individual objects like the star itself. You can see its properties and they are listed on the side. You can click each of the exoplanets. There's like this Neptune-like planet orbiting that particular star there. And you can click like some interesting data. For example, you can click like how long would it take me to get to this planet, like driving at 60 miles per hour. So it's like, hey boss, I'm going on vacation to this super cool exoplanet I found. See you in 2 billion years, right? It doesn't sound like a short trip, right? That's actually the one way, and then you have to come back. Probably 4 billion years more. Probably the Earth won't be here because we would be eaten by the sun when it becomes a red giant, probably, right? So not only your boss won't be here, but the entire planet will disappear. So what if we take an Uber with the Voyager spacecraft, which is the fastest spacecraft we've ever built? It's like it was traveling and it's still traveling at 38,000 miles per hour. So 1,000 times faster than a car. And with that, to this exoplanet, you get there in 3 million years. 3 million years ago, we were not even like humans, right? I think it was Australopithecus probably, right? So imagine like 3 million years in the future. That's like the fastest we can go to this exoplanet. So I don't think SpaceX will be offering any rides in anytime soon to get there. Not even at the speed of light, you would get there in any reasonable time because it would take you 175 years at the speed of light, which we know we cannot do. But it doesn't prevent us from studying these planets. And we can study them from the Earth, and we can actually know what they are made of. So how come to be that we can know what the composition of an exoplanet is from here? So we basically built models, and I stepped into these two papers when I was starting my PhD. That was like 2010. In this paper was published in 2006. So this was recent for me. That was when I was doing my undergrad. These papers were reporting the first ever model for the internal structure of an exoplanet. So this was cutting edge science. And I was like, how did they do it? It's like, what do you need to know in order to do this? And well, inside the paper, I see first the report that there have been 400 exoplanets reported to exist outside our solar system. And remember that number, because I will ask you later. And in addition, they basically put this figure where they basically show a layered planet. So they choose some materials to build this exoplanet that they know the mass and the radius. And they are trying to match that mass and radius with different compositions. And they basically solve some equations, but they depend on the material properties that the planet is made of. And again, material properties are pressures that nobody has ever seen, nobody has ever studied. So they didn't know what to put in those equations because there were no experiments and no calculations. So there was a need to connect mineral physics now with exoplanetary science. And they basically plug into this set of equations. You don't need to understand them, but basically here, the relationship between pressure, density, and temperature was what they needed to close that set of equations. And that comes from material science. So this is basically where my research lies. It's in the intersection of these three main areas. It's basically doing high pressure physics, where I study solid phase transition, solid liquid phase transition at really high pressures. And I choose materials that are relevant to planetary science to understand different phenomena that can be occurring at these same pressures. And this somehow connects with warm dense matter, which is a state of matter that occurs usually at the envelopes of white dwarf, for example, where the material is so dense that even at thousands of degrees, you can have solid material. So this is more or less what I will be talking about today. And behind all this is this technique called density functional theory, which is basically solving the quantum mechanics problem of a set of electrons and atoms interact. So let's go back to planets. So what do we understand by planetary formation? We know more or less that planets accrete in a disk where there's a lot of material going around the disk, a lot of pebbles that accrete. And when the pebbles get together by sticking to each other by electromagnetic forces at the beginning, they start attracting more and more rock due to gravity, and they start like a rapid accretion. And at some point, you end up with an extremely large planet, like dozens of kilometers wide, that is completely molten. So this is the magma ocean phase of the planet when it's forming, where so much energy has been delivered by the impacts that the whole thing is molten. And this thing at some point starts cooling down, and things start to differentiate, to separate, different chemical processes occur, solidification starts at different regions of the planet, and that's what we want to investigate from the mineral science point of view. So astronomers detect this by basically looking at a star and seeing how the brightness of the star decreases when something passes in front of the star. So sometimes that can be another star. There are binary systems, so you have to discard that one. But then after a couple of turns, you can detect the size of a planet with this method. And not only that, but also the composition of the atmosphere of that planet that is passing in front of the star. And with this other method called radial velocity, where you see the absorption lines that tells you like what the star is made of, they move a little bit because the planet is like tugging from the star and it makes it move. So this Doppler shifting lines motion basically can help you to infer what the mass of the planet is. So with mass and radius, we can start building models of what the planet can be made of. So this was the Nobel Prize that was awarded in 2019 to Didier Queloz and Michael Mayer due to the discovery of the first exoplanet in 1995. So this science is basically 25 years old, 30 years old, right? So it's very new, and we are just starting the discoveries of exoplanetary science. So it was in 2022 when we increased the number, remember, 400 exoplanets to 5,000 now. So when I started my PhD, there were just 400. Now we have like more, almost 6,000, like when I checked last night. And these planets are really interesting. And with the new technology, for example, from the Webb telescope, they are able to detect what the composition is, like many different molecules that exist in the atmospheres of these exoplanets. And carbon dioxide has been detected. And as carbon dioxide gets detected, they can detect other molecules, and astronomers are actually looking for biomarkers that can tell you, hey, if this gas exists, probably it can only be generated by life, not by geological processes. And that's what they are after. They are about the serious question of, is there life in other planets in this way? If you can detect something that can only be generated by life, then I think you get not only the Nobel Prize, but you will be in the news for it, right? But it's hard. It's hard because there are many gases that can be generated by natural processes and not necessarily by bacteria, right? That would be like the first approach. So the planets that they have discovered come in many categories. We have planets that look like Jupiter, or gas giants. They're terrestrial planets, but very interestingly, the most common planetary types are super-Earths and sub-Neptunes, and we don't have any of those in our solar system. They are the most common planetary types, and they lie basically in the radius between the Earth radius and Neptune radius, which is basically 4 times as big as the Earth. And they come in this distribution that tells you there are many that have like this size and many others that have this other size. And we have no planets between the size of Neptune and the Earth. And we wonder why. why is our solar system so special? Is our architecture not the traditional one? It seems like the statistics show that, yeah, we are the weirds in the neighborhood, right? Our solar system is not the typical set of sizes that nature produces in other solar systems. So far, the statistics show that 1/3 basically of the planets are like gas giants, another third are super-Earths, and another third are sub-Neptunes, and just a tiny fraction are planets like the Earth that are, we think, terrestrial. So I already told you that astronomers can give us mass and radius. They can measure it to very accurate precision. They don't have it for all exoplanets, but when you have the mass and radius, you can start building these models I told you about. But what do you put in those models? How do you know that what material is reasonable to put in the model? Because it's an assumption that you have to take. Is it reasonable to put a uranium core for a planet? It doesn't make any sense because it doesn't correspond with anything that we see. So where do we get this information? And the way we get information about this is meteorites. So we get these gifts from the sky of things that have been orbiting the sun for billions of years, untouched, which are pristine samples of what the solar system looked like when it was just forming. And they just happen to fall on the Earth, and they tell us what the materials were around the sun when it was just accreting planets. So you send the samples to a lab. In this case, this material is a palisade that is not that common. People believe that it comes from the core mantle boundary of a protoplanet because you need really high pressures to generate these phases. And you characterize more or less what is the mineralogy of these things, which is very different to the minerals that we find on Earth. And then you can have a very good clue on what to put in those models to start solving this equation. And that's how we figure out like what planets could be made of, because the mass and radius, and we have probable compositions. Okay, so there are many types of worlds, as I showed you earlier, that have been classified, for example, in lava worlds that are so close to the star that the surface of the planets is always molten, is tidally locked, so it always looks at the sun. So the phase that is facing the sun is roasted, is evaporating sometimes. So now in material science, it became relevant. The question is like, what is the boiling point of rocks? Imagine that. It's like, what is the temperature you need to boil a rock? And this is something that is actually happening in some of these exoplanets. There are ocean planets, there are hot Jupiters, there are cold giants. So the dynamics inside these planets, all these planets is different. The types of materials that you find is different. So you have to address each of the planets by context. So this combines several fields of science, as you have probably seen, because you need astronomy to tell us about the planets, but also geophysics, chemistry, and thermodynamics to understand the processes that occur in these conditions. And of course, we need to push it to these new pressures that nobody has explored before. So there have been many systems that have been studied. TRAPPIST-1 is one of the most studied exoplanetary systems. And as you can see here, they all orbit, the 7 planets, in an orbit that is tighter than the orbit of Mercury. So like all these planets are super close to the star, and they're happily orbiting there, and they are stable as far as we can tell. So this defies all the conceptions that we have, like how close planets should be to their stars. There are planets that the entire year lasts a day. It takes 24 hours for a planet to go around their star. We don't have anything like that in our solar system, right? And going back to the Earth, like how do we know about planets? It's because we have studied the Earth so much for obvious reasons, right? We're standing here and we have something that you probably have never thought about that the Earth does itself. It's seismic tomography. We can use the earthquakes to know what is inside the Earth. And this basically works in the same, it's like the same principle as when you go to the hospital and you get a tomography, when you get x-rays scanning all your body. It's like rays penetrate your body and they can tell you what's inside you. It's the same principle. The earthquakes generate waves that travel through the entire planet in different directions, and some of them travel through the core. And it turns out that certain part of the signal, like the S waves, you probably have heard about the P waves and the S waves, the S waves cannot travel in liquids. And that's the first evidence that we have that the Earth has a liquid. And that's how people demonstrated that it also has an inner solid core, and that is made of iron. And then it again connects with the properties of material, because the seismic wave velocity, the velocity at which like waves propagate in materials, depends uniquely on the material itself and at the density at which this material is. So I can do predictions, taking some minerals and doing quantum mechanics calculations, what the velocity will be, the sound velocity will be in that material at that particular depth. So I can help the seismologists build an entire model for the Earth to figure out what are the candidate materials that are compatible with this, all the seismograms that they read through the entire planet, and figure out what's inside in each of the separate layers. So it's a really collaborative effort to try to figure out these things. And we've learned so much for the Earth that we are now extrapolating into other planets. So fun fact about the Earth, you probably know that the Earth is 4.5 billion years old, right? Does anybody have any idea how old the inner core of the Earth is? Who takes a bet? It's like 1 billion, 2 billion, 3. Was it born yesterday? 8 billion. 8? Well, it cannot be older than the Earth, right? So it's like tops, like 4.5. But it was born immediately after, a few million years after. It turns out that is very recent. It's actually just 1 billion years old. So for most of its life, the Earth did not have an inner core. And this has direct relationship to the material properties, like how minerals crystallize at different temperatures and pressures. Okay, so again, mineral physics helps understand these processes. So there are a lot of processes happening inside the Earth, and one of the most common things that geophysicists know is the convection of the mantle. And here's something that you should take from this talk. Fluid is not the same as liquid, because both solids and liquids can be fluids. You can have fluid motion because things flow regardless on which state of matter you are. So this is convection in solid state. All this thing is solid. It's just, it takes like thousands of years for this thing to move like these distances. But if you like press fast forward, this is more or less the picture that you have for the Earth interior. And this process occurs at constant entropy. So that's a constant from thermodynamics. So it means that you need to know thermodynamics to understand this thing. And actually, if you find it like not very familiar, I suggest you to take a look at your miso soup next time, because it's doing exactly the same thing, right? You can literally see the convection cells of the parcels of hot fluid coming from the bottom and rising to the top. And this is a process that occurs at constant entropy, and it's basically the same that is happening in the Earth. This is just much faster, right? So there's active research in understanding not only the Earth, but how like these inner processes, how the interior affects the habitability of exoplanets. And what do you mean by being habitable? It has been a question that's being put forward because we realize that we don't know what we mean by habitable. It doesn't mean necessarily that there are humans. So you say, okay, maybe that there are bacteria, that there are trees, but do you really need water? Or do you mean like the distance from the sun? And then there are sets of criteria that you have to fill in order to call the planet habitable. And that's a definition that we still cannot agree on. Okay. And there are many papers that have addressed this question. What's the connection between the interior of the planet and the habitability, and how the density and not the radius separates like the type of planets that you can have, whether they're rocky or like Neptune-like. And it's a very, very active of research. So we're still making so many questions. There are so many things we don't know. So we have to investigate this from different angles, different fields of science. And one of the studies that I wanted to show you was done recently in Livermore. That's why I mentioned Livermore at the beginning, at this National Ignition Facility, where they have these gigantic lasers here. And they're basically a facility that puts together 200 lasers that have like extremely high powerful. They're the most intense lasers in the world. This thing is like this thick. It's like tubes that looks like water pipes, but it's just light, a gigantic laser light 200 beams trying to get into the sample that is inside that chamber that you look in the back. You can see here the comparison with the size of a person here. So this thing is huge. It's like a building tall. And then all the lasers, 200 of them, are designed to arrive at unison at the center of this capsule, where they meet a sample that is tiny, like smaller than your eye pupils. It's millimeter size, and it gets crushed by the X-rays that arrive to this chamber through the two pinholes that it has at the bottom and the top. And this radiation that is condensed and trapped inside this very, very tiny capsule starts compressing a material that is usually deuterium and tritium. And the whole experiment lasts 20 billionths of a second. It's like nothing. That's like 20 nanoseconds. And in that time frame, they have to measure everything that's happening in the material. Like if the material went to liquid, at which temperature did it go, which pressure did they have? And they reached ignition just in 2022. That was really recent. So they were about to be called the Never Ignition Facility until they really played the name of the National Ignition Facility. It took them decades to reach to this point. And the cool thing is that they are now using the lasers to compress minerals that now are relevant for planetary science because they can explore these insane pressures that we've never seen before materials have. So one of the materials what I like to imagine is Goku sending like this spirit bomb over material to crush the material at the really, really insane pressures and temperatures because it's like this all energy arriving to a material. In this case was iron, which we think it's at the center of every rocky planet. And they basically launch a shockwave with this laser. The lasers generate a shockwave that propagates through the material like this. And this new state of matter is at a really, really high pressure, really high temperatures and densities. And they can measure like what's happening with the material itself. So what they did in this experiment was basically to compress until the material melted. And then they kept compressing until the pressure solidified the material. And since they can do X-rays to figure out what's inside the material, they were able to prove basically that the material transitioned from a liquid to a solid. So they could say like this, okay, this signal, well, they know what they're doing, just believe me here. This signal corresponds to a solid, and not only a solid, but what solid was crystallized, which in this case was the hexagonal phase of iron. So that's like all they can know in just a tiny fraction of a second, just few nanoseconds of the experiments, and they can figure out at which temperature the material melted for a given pressure. So that's connected to planetary science, and we want to know if we can predict these things from simulations. So here's where I come, and I do my quantum simulations. I can predict the shock states. If I solve some equations that belong to thermodynamics, I can predict at which pressures and temperatures you will get if you shock the material with certain velocity. And that is being very successful in the past. So you can see the agreement with the line and the points. It's basically my predictions here in these papers with the experiments. So it's beautiful agreement. So we believe that our simulations are really predictive, and we applied it to this case of iron to understand the crystallization of the core. And basically, we wanted to know when this whole thing will crystallize entirely, right? We were only focused in the core here, not in the mantle, but eventually this thing will crystallize any planet. So what we have to monitor here is this concept of the adiabat that you just imagine is like how the pressure and the temperature increase as you go deep down in the planet. So the more you dig into the planet, the higher the pressure and the higher the density. And we know more or less how this behaves. And if this intersects the liquidus, which is the temperatures at which a given material crystallizes, then you will have crystallization of that particular material. So as this profile of the planet comes down, you will have crystallization of the core as this line intersects the melting line of the material that you're interested in. So that's what we calculated. Basically, in this crystallization that we call bottom up, we want to figure out where this melting line is respect to the planet profile. So we did some calculations. I won't go into this, but basically it's like energetic evaluations. It's like when does the solid have the same energy as the liquid? And we can skip that and you can ask me later, but it's just an energy calculation. And what we figured out are these blue points here, which is basically what is the melting temperature of iron for a given pressure that is really high compared to the Earth's pressure. And what you can see in this plot, which is kind of busy, but with the red squares in the background, is beautiful agreement with the experiments. So I did not use any feedback from the experiment. And with my simulations, I was able to predict the same thing that they measured in the crazy experiment that I showed you earlier. So we basically validate our simulations and we say, hey, let's use it for something else. I reobtain the melting line that you report. So I'm confident on that. I will do something else. We'll skip that. But I can calculate these curves called isentropes, which are these planetary profiles, and figure out when a super-Earth will start crystallizing in the core just by intersecting it with the melting line that I just obtained. And basically what I figured out here is that these exoplanets, these super-Earth, crystallize in the same way as the Earth because they crystallize from bottom up, from the very center upwards. It could happen, and it happens for some materials, that the pressures allow the crystallization like top to like, what to say, like inwards, right? From the surface inwards. In this case, it happens bottom up, and you don't know until you analyze your materials. So this is really, again, another active area of research because we don't know the properties of the minerals at these conditions. We have to investigate. So we built these models, again, that I showed you at the beginning. We put a silicon mantle there. And what we found was basically that these super-Earths, these planets are so massive that the melting temperature of iron at these pressures is so high that it's very difficult to have a liquid outer core. And in the Earth, it is the liquid outer core that is generating the magnetic field, right? So if these planets have a completely frozen core, there's no liquid, then they don't have magnetic fields, and probably there's less likely that they will have life because they won't have a magnetic field that is protecting them. So there are many assumptions that I did here in this study. This is very simplified, but we can already make some conjectures based on real physical studies of what will happen with these planets in terms of the magnetic field, for example, and on these crystallization processes. So that's how you connect the interior of a planet with what is happening on the surface. So there have been like very cool experiments that have been developed Livermore again in the National Mission Facility, but also in SLAC, which is in Stanford, where they have crushed different types of materials. And in particular, ones they did polystyrene, which is this material that you make these cups from. And it's basically carbon and hydrogen atoms forming these molecules. And when they shocked these material, what they basically did was to rip apart the entire molecule. All the bonds between the atoms were broken, but the carbon remaining, the red atoms, were at such a high pressure that they formed diamond. And they literally obtained diamond from plastic in the experiments. Now, this won't make you a millionaire because they are like tiny nano diamonds, and the experiment is way more expensive than the diamonds that you get. So it won't be a factor you can get money from. But at least proves the principle, right? That matter is made of atoms, and carbon atoms at high pressure make diamond. And they literally observe that. They have evidence of this. And this is not only important for material science and chemistry, but it has implications for planetary science because now we can say that there's diamond rain in Neptune. Why? Because the composition of Neptune is very similar to polystyrene. It's a combination of carbon, oxygen, nitrogen, and hydrogen. And at the conditions that you find in the interior of Neptune, it's very likely that the same process occurs when you rip apart all the molecules and you leave the carbon behind it. That forms diamond. And that you can connect it to, for example, the evolution of the heat escape of the planet, like how the planet is cooling down and why Uranus seems to be like less heat flux coming out of the planet compared to Neptune. And we thought that they were made mostly of the same things, but from Neptune, there's way more heat escaping than from Uranus, and we still don't know why. And maybe this is an explanation because there's this diamond rain that is preventing the heat to escape. Who knows? We still have to do more research. And this is actually a very active area of research. This is just from last year where they tackled like the problem of the diamond rain in Uranus and Neptune. And they keep publishing papers on this, not only from experiments, but also from the DFT simulations that I do. These simulations of atoms with quantum mechanics at high pressures, where they couple it even with machine learning to accelerate the process, such that they can investigate at which concentrations, pressures, and temperatures you will have like this dissociation of the molecules and formation of nanodiamonds in the pressure temperature space. And then you compare it to planets to figure out if that process applies or not. So it's, again, a very active area of research. There's so little we know about it. There's so much to do that this is really exciting. Now, another type of planet that I was involved in studying was Jupiter. So Jupiter is very cool because it's the largest planet that we have in our solar system, and it's made of gases, right? That's what we heard probably. But as I showed you in the video at the beginning, it must have formed from a rock that accreted all that gas around it, right? Yes?
Sorry, your battery is low.
All right. Okay. Thank you. Thank you very much for that warning. Yes. Is that working on you? Okay. So Jupiter has this layer of metallic hydrogen, which is something that you probably have never heard of. So hydrogen at ambient condition is a molecule, right? It has two atoms, they vibrate, and they form this diatomic molecule. But at the conditions of Jupiter, the molecules are so close together that the concept of a molecule disappears, and you just have a bunch of atoms like migrating around, and you form a liquid of hydrogen that is denser than water. So it's basically an ocean of metallic hydrogen that you can, in principle, sit on and navigate on. But the pressures and temperatures are so high that you will die instantly. But in principle, you can put a ship there, right? It's very deep down below the planet. It formed after the entire planet was actually put together because it was accreting gas at the beginning and the metallic hydrogen formed later. And we put the question, is it possible that this metallic hydrogen could have acted as a solvent for the rock that is at the center and formed the planet to begin with? So we're talking about doing chemistry at insane conditions of pressures. We're trying to solve basically the problem of water dissolving salt, but at millions of atmospheric pressures and thousands of kelvins of temperature. So how do we even tackle this problem? What can we do to do chemistry? Well, we put a likely scenario of solubility, and that requires us to do simulations of atoms where we have a certain material. In this case, we chose sand, silica, dissolved in metallic hydrogen here, and basically calculate if the energy of this thing, of the dissolved system, is higher or lower than the energy of the parts. That's all the thing that you have to take from this equation. So if it lowers the energy, the reaction happens. If the energy is higher, the reaction doesn't happen. And that depends on the pressure and temperature you're at. So basically, we span the space of pressures and temperatures to see where this reaction could form. And we found that at all conditions of Jupiter interior, this reaction would be very favorable. And not only for this material, we did it for water, we did it for magnesium oxide, for MgSio3, it's another rock. Everything dissolves in metallic hydrogen. So it seems like this metallic hydrogen is a really good solvent of rocks in the same way that water dissolves solids, okay? So that has completely changed our picture of the interior of Jupiter, because rather than a compact core, we now believe that Jupiter has a diluted core that extends all the way to like 50% of the radius of the planet. So this diluted core is basically contaminated metallic hydrogen that is actually generating the magnetic field of this planet. And that is not only our prediction, but it matches what astronomers have observed at NASA, because they published this paper where they say that this Juno spacecraft that is measuring in Jupiter. It went there, it's orbiting currently Jupiter, measuring the gravity field and the magnetic field. The measurements indicate that the gravity field necessarily implies a dilute core. So the numbers that they measure for the gravity field require that the core is diluted and not compact in a very tight region, but it's rather spread out through the interior. So you can see how the power of the simulations can actually predict things that validates what we're doing. So we're really doing really great progress in the field, and we're pushing it forward. So I want to tell you now about water worlds, which is another category of planets. And here we have Europa on my side, right? Like turning around. The moon of Jupiter, Europa, is almost like the Earth upside down because the oceans are below and the floor is above, right? So it's just that these are not rocks. It's mostly like brine and like salty material, but mostly made of ices that is on top. And you have like this plume of volcanoes of water that is literally extruding water to the surface that they have seen. And people believe that there could be life inside this moon of Jupiter because the conditions to have liquid water here are the precise conditions that we find on Earth. It's just that this thing is like, I think, 20 kilometers deep down. And if it's hard to dig here in Earth, imagine going to dig in a different planet, in this case, a moon. It will take many years to get to this ocean, but eventually we will do something. And for this, I actually recommend a movie that is really good. It's called Europa Report. It's a little bit sci-fi, but it gets more or less the idea right. So the astronauts go there and start actually landing in Europa, and they find like really cool things. They're trying to find life in the ocean below. So anyway, we wanted to focus on water worlds, but not in our solar system like Europa. We wanted to find out these water worlds that astronomers have discovered in other planetary systems, exoplanets, that can have up to 50% in mass of the planet. It's just water. So the density of these planets is so low that you cannot explain it by having just rocks and iron. It must be like very light material around, and it's not an atmosphere of gases. So it must be some type of combination of ices. And to give you an idea of like how little water there is on Earth, and sorry, I wanted to say this first. We wanted to explore basically if you have a layer of ice in these planets on top of the rock, what would be the interaction between the rocks and the ice in these planets? And at these pressures, this phase of iron, of water that is called super-ionic appears, where you have the hydrogen atoms flowing like a liquid in a lattice of stable oxygens. So this is no longer a water molecule, H2O. The stoichiometry is still H2O, but there are no molecules here. So this is kind of a solid, kind of a liquid. It's just a new phase of matter that we have seen in experiments now, but nobody hasn't studied deeply. So we believe that actually super-ionic ice is the most common type of ice in planetary interiors because the planetary interiors are way more broad than the conditions that you find on the surface and the materials that you can find on surfaces. So this is a black ice that is at insane temperatures, like 20,000 Kelvin, and it remains in this state that is kind of solid. So yep, black hot ice might be the most common form of water in nature. So now what I was trying to get across is that to have an idea of how much water there is on Earth, imagine the Mount Everest, which is about 11 kilometers in height, or the Mariana Trench, which is 11 kilometers going down on the ocean. It's like the deepest part of the ocean. They're about the same height. That is nothing, but literally nothing compared to what's below the oceans. So the oceans in radius occupy just 0.2% of what is the radius of the Earth. So if that's 11 kilometers, you have 6,000 more kilometers down there. So the Earth is not a water planet. Water is just like a makeup. And if you remove your makeup, you're basically the same person. It's the same with the Earth. The Earth, if you remove all the water and all life, is still the same Earth inside. Water is very little in abundance compared to the amount of rock that we have below. So is really like makeup. So what we did in this project was try to smash this type of water walls with a lot of water in them, again, like 50% biomass, and see what they would do. So they would form like these layers of water and rock, but there's no chemistry involved in these type of simulations. They just tell us more or less what are the pressures and temperatures we could reach in these formation events. So what we did next after simulating these formation scenarios was to literally put water on top of rock. And this is a project that was done by Tanya, who's joining us today, a student in our group, that she discovered basically that these rocks and water become miscible at these conditions, like extreme pressures and extreme temperatures. These materials form like a new mush where everything is homogeneously mixed rather than two separate liquids that separate in droplets like water and oil. They are not immiscible liquids. They completely mix and form, we believe, a new layer in the planet that is not very clearly defined. So again, this has changed our picture of what we think is inside planets. So rather than having separate layers, we think now that there's this blurry interiors where you have like a gradient of composition, which actually makes things much harder to study, but it puts us in the right direction, more realistic. And finally, I wanted to tell you that something related to the magnetic fields of the planets. You probably have not seen this, but not all the magnetic fields that we find are dipolar, meaning that there's a north magnetic pole and a south magnetic pole like in the Earth. You can see that Ganymede, this moon, has also a very dipolar field where you can clearly see a north and south. With Jupiter, there's like some oddities, but still clear north and a clear south. Saturn is very, very dipolar, very symmetric, but something happened with Uranus and Neptune. So when they're giving up the dipolar fields, they got late to the party somehow. And they didn't get dipolar fields. For some reason, their magnetic fields are weird. So all the magenta sites are like north, and all the green sites are south. So there's no clear north and south. It's just like this multipolar field. And we have no idea why it happens like this inside these planets. So how is this connected to the composition of Uranus and Neptune? And what is generating actually? What are the materials that are generating this magnetic field? Because it has to come from the inside of the planet, right? And what are the pressure and temperature conditions on which this field is generated? All these are open questions, and we don't know why still the magnetic field of these planets are so weird. So we delved into this investigation of studying hydrocarbons, and another student in our group, Kyle Davila, found this new state of matter that we coined double superionicity. If superionicity was not enough, now we have double superionicity. And what we found basically was that not only you have hydrogens flowing like a liquid in a lattice, but also you have a second element, for example, nitrogen flowing like a liquid in the lattice. And why is that relevant? It's because when you have atoms that carry charge that moves across, that charge can induce magnetic fields when it moves. That's how the Earth generates its magnetic field, is because the charges in the liquid core, they move and create the magnetic field we have in the surface. So maybe these new weird phases of matter that we've never thought about before are the reason why the fields of Uranus and Neptune are so weird. But we still don't know. There's so many open questions. There's so many materials that we need to investigate in order to finally answer that question. So again, this field is just growing. So I'll leave you that with a summary and a QR to my website. Feel free to reach out. This is my mail. I'm happy to take like any questions. And thank you for coming to my talk.